The University of Northern British Columbia is more than just one campus here in Prince George. I mean, you might know that, but did you know what they have behind the walls in this building? The Wood Innovation Research Lab, otherwise known as WIRL, has a lot going on. And we're going to learn about it today on the show. Let's go inside and meet Mike, the senior lab instructor here. Yeah, now inside the big building downtown, the Wood Innovation Research Lab with the University of Northern British Columbia. And Mike, nice to meet you.
Nice to meet you, Caden.
Yeah, thanks for having us here. Tell me a little bit about what you guys do inside this building.
WIRL, our Wood Innovation Research Lab, we do wood research. So
I guess it's self-explanatory a little bit.
Anything you can think of, if you can build it, we can break it. But a lot of our research actually goes into informing code developments and everything. So the CSA OD6, the Canadian Wood Design Standard, a lot of the new implementations have been developed partially here, other labs. Wow. But yeah, we do full-size testing here, two-story buildings as high as we can go, or tiny little small component testing, as you will find out shortly.
Wow, okay, there's going to be a little bit of a, show and tell element today.
Tell,
I like it, just like everyone's favorite day in school.
Yeah, test your little, your handy skills a little bit.
This is true. So how does this work into the construction side? So you guys would test it here, and then they know this is going to work if they're building a building, is that?
To an extent, yeah. There's a lot of buildings going up that are really innovative in terms of use of wood materials and systems. So oftentimes engineers come up with an idea, they design it, yet haven't had the clue really, will it work, could it work, it should work. So oftentimes they send then 2-3 samples of what they're designing and test it here to verify that what they actually designed will have a chance to stand up.
Oh, cool. Okay, so it's like a thesis. Like they send you like, it should work, but can you double check?
So to speak, yes. Because a lot of stuff is actually sort of borderline code, not in a bad way, but in an innovative, in a really innovative sense. And you make a certain type of assumption. Every now and again, you want to really make sure those assumptions are reasonable.
Well, last time I checked, Mike, building things is expensive. So you want to make sure it works.
Exactly. Even more expensive if you have to rebuild them.
Yes, this is true. And no one wants that to their name.
No.
But tell me a little bit about what you do here, because you've been here for a while.
I've been here since the wood engineering program started in 2014. I'm a senior lab instructor. I teach prefabrication, BIM, CAD, but also project design, so real life design projects with students. I'm also happen to be the lab manager, one of the reasons you meet me today.
Okay.
And I'm trying to keep everything in line here. Oftentimes not as easy as it sounds, but
Herding cats? A little bit?
Kinda, yeah.
So what made you want to choose to work here in Prince George for the university?
I mean, the program is unique in Canada, North America, really. That was a really big draw. And I didn't really know Prince George that well initially, but I'm certainly glad I came. Like, if you outdoorsy, kind of like me, I'm done, I'm here.
Yeah, so tell me about this uniqueness in Canada here, because I don't think people realize this. Like you're saying, other universities will talk to you and be like, oh, can you help us out? Because this is not common, what you guys do.
That is correct. So from an academic level, in North America, a lot of engineering programs, they have one course, maybe 2 courses on wood design. We implemented in our undergraduate teaching, but we have a fully dedicated wood engineering program on the master's level. That is completely unique. Nobody else has that. There are some micro-credentials starting to pop up, but in terms of a fully a fully running program, we are the only one in North America. Wow. In terms of the lab, our big selling point is that we have a lot of testing capacity with strong floors, strong walls, UTMs, universal testing machines, but also a fully equipped workshop. So we usually, or not usually, but we are able to make our samples. So we don't have to have everything ready-made shipped, which is a huge bonus.
Of course, and the building itself has a little bit of a story now.
The building has a story too.
As people can see the scar.
There's a scar behind us here, yes. I mean, the story of the building starts at the fact that it's a certified passive house, so it's a very, very energy efficient building, which it sort of proved to a certain extent with the fire next door, or an explosion at first.
Yeah, you undersold it there for a second.
Yeah. I mean, we sort of said, or the engineers that actually built and designed the building, they were saying this building in one instance had to go through an explosion, which is similar to an earthquake, a fire, and the flood afterwards from all the firefighting. So it's been battle tested, I would say, and it stood up well.
Oh yeah, I don't know if you were part of the team that put this all together, but mission accomplished.
Mission accomplished, yes. I was part of the team trying to get the testing back in, yes.
Okay, well, so mission accomplished.
Mission accomplished, yes.
Okay, well, we're going to continue after the break here to learn a little bit more about the WIRL and what they do here and demonstrate it ourselves here. You got a little project.
Yeah, we got a project for you.
Perfect. I like this so far. Thanks for this, Mike.
There you go. Now we're just starting to squeeze and pull. And
So the experiment's done.
The experiment is done. You actually see it pulling off.
Oh, yeah.
Yeah.
Wouldn't you know it, we're in the Wood Innovation and Research Lab, and we're going to do some wood research. That's what we're doing?
That's what we're doing.
Perfect.
We're going to start with a bit of connection research. We prepped one sample already. Full disclosure, we wouldn't normally do two different things on one sample, but let's call it a little tug of war of two types of connections. So we have a bolted connection here, one's with a larger amount of smaller diameter bolts, and one with fewer large diameter bolts. The idea being that if you have a larger diameter bolt, they will take a little more force, but they fail kind of explosively.
Gotcha.
Versus a smaller diameter bolt will kind of bend and yield a little and give you a little stretch. That's why you use more to get the same forces on the other side, yet you don't fail explosively.
Interesting. And you call this a dog bone?
That we call that a dog bone because we need the center a little narrower than the top because we don't want to fail the top.
Big dog for Clifford.
Yes. And then we will get you to assemble the second test. Same thing, tug of war. We're going to use 6 screws that we install. I'll put it on that side, you can see it.
Yep.
90 degrees. So they're going to act similar to these bolts. And then we have a slightly longer screw that we will install fewer of. On the other side, these screws are very, very strong in withdrawal. So bending, but in withdrawal is really where they shine. So we install those at 45 degrees.
Gotcha, yep.
And again, our tug of war will be 6 90-degree screws versus 4 45-degree screws. So
it's always my favorite day at school, Mike.
there you go.
All
Then
right.
we're gonna move on to a little bit more materials testing. We have 2 different species again. We have, not again, these ones are the same, but
same,
Douglas fir and
little bit of spruce.
spruce. Yep.
I'm
so
ready.
let's get you set up for your shop class here.
Here we go. If you got attachment issues,
Yeah.
this ain't the place.
Nope, that ain't the place. You can be proud of your work, but it's gonna be broken.
It's gonna be broken.
That's 6
That's
out
good
of
enough.
6. All right, so now we have to fire up the brains.
Oh, the brains. There's a computer.
So it's a little
It's gonna-
anticlimactic, but so you can see
It's moving.
you can see the load go up. 1.2 millimeters displacement, 8 kilonewton. A kilonewton is roughly 100 kilograms.
Okay.
So we split the bottom a little bit.
Yeah, a little bit.
Yeah,
That's bad.
that's not. Yeah,
That's a fail.
that's what you normally don't want to see.
Okay. And now, how would you rectify that? How would you fix that? More bolts?
These screws that we put in, they're actually supposed to prevent that to a certain extent. And I mean, they probably did a bit, but not enough. Yeah. So now we have to see if we didn't bend the bolts so we can get them back out.
Fire in the hole.
And we are running.
We're running.
Slow and steady wins the race.
Yeah, you couldn't really just like, it wouldn't.
Well, it wouldn't really,
What's the point?
show. When we do testing, we already adjust for it in our calculations for it being faster than it would normally be loaded. Oftentimes, you know,
You're doing it over hours.
And it's people walking in and out. It's like you don't have to full load on it all the time and not instantly. You're slowly loading things up. Grabbing,
now we're failing.
and now we're just starting to squeeze and pull. And
So the experiment's done.
The experiment is done. You actually see it pulling off.
Oh, yeah.
Yeah.
Interesting.
Yeah.
Now we're turning around the camera to meet Mr. Houman. Hey, nice to meet you.
Nice to meet you.
Yeah, PhD student here at the University of Northern British Columbia in WIRL, and you are doing some tests today. What are you doing?
So what we're doing here is doing withdrawal test on cross-laminated timber. It is, as you can see, is tilted because The way we had this in the actual test that we were doing on point-supported CLT, we use self-tapping screws to reinforce the resistant mechanisms. Now we want to know how strong the screws actually are to use it as the input value in the model that we are working on. So you can operate the machine.
You want me to operate? Well, it's
Yeah.
your test.
Oh,
you
go
sure?
ahead.
Okay. What am I going to do?
So you're just
Start.
moving up the not yet.
Okay, don't hit start yet.
Yeah.
Okay.
Just move up the crosshead
Move up the
a little
head?
bit. Yeah. Just watch this.
Okay.
Oh,
Oh, did I just ruin it?
kind of.
Oh, no.
But it's okay. It's okay.
It's okay.
I've got more samples. Don't worry.
Oh, no. What did I do? Did I go too fast?
So yes, you went too fast with the fast jog.
I should have done slow jog.
Yes. Oh, it's okay. It's not a problem.
Houman, as you can see, the nicest guy in the world. You should fire me. Tell me to go home. I'm going home.
Put this bar across and essentially pushing this bar in.
Compress it.
So think of this at the bottom plate of your house framing,
Okay.
sitting on the concrete wall, fully supported, and that may be a stud or something trying to push into it.
Okay.
So as we see how the bulges too,
Compress it. Yeah. Wow. That's crazy.
yeah, and then start splitting the ends. And I don't know if the camera can pick up how it bulged
Yeah. Oh.
out on that side.
Oh yeah.
It
Okay.
got wider.
Yeah. Yeah. I see it now with my
So
eye.
we compress the fiber, condensing them, making it stronger, but we also sort of increase the surface area, which also makes it stronger.
This has been so much fun today, Mike. Shout out to Houman as well, behind the camera here, hanging out with us. I learned a lot, and you definitely can too. Definitely, if you're interested in this kind of thing, check out the University of Northern British Columbia. Great addition to the Campus Connection today. Thank you for your time.
You're welcome. Thank you.
Campus Connections is brought to you by the University of Northern British Columbia, where the North inspires new ways of thinking.